Hello, welcome everybody. Thank you all for coming to the welcome to the last of our 3 sessions on things that actually exist in the world. I'd like to invite Jenny Cheng to talk about 3D printing anywhere with the Blender API.
Good afternoon, everyone. I hope you're having a good conference so far. It's going to become a great conference in just a moment because you guys are here at 3D Print Anything with the Blender API. My name is Jenny Cheng. I'm a software developer in New York, and I do a lot of 3D printing as a hobby. So for the next 30 minutes, I'm going to share that hobby with you, so hopefully you can go out and start making your own creations. You might have heard about 3D printing before. 3D printing is an additive manufacturing process. What this means is it builds an object up layer by layer by layer. You can contrast this with other manufacturing processes, like CNC machining, where you take a block of material and cut away at it to leave your final object. There's a lot of different kinds of 3D printers out there. They use different technologies like lasers, extruders, which are squeezing material through a little nozzle, and binders, which sort of use a glue-like material to bind particles together. You can 3D print in a lot of different materials, like plastic, metal, and even ceramic. There's lots of possibilities. It's really good for rapidly prototyping objects or making very custom objects. 3D printing is not a new technology, but it's one that's become readily available to consumers. With the rise of desktop 3D printers and online services where you send them a model and they'll mail you the model back 3D printed, all you really need is a 3D model to get started with 3D printing. So let's talk about 3D models. There's a lot of different representations of 3D models. One common representation is to represent your 3D model as a set of vertices, edges, and faces. So this 3D cube we have here has a lot of vertices. The vertices are the corners of the cubes. Each vertex is a point in space. It has an x-coordinate, a y-coordinate, and z-coordinate. The edges are what connects two vertices together. In this example, they would be the edges of this 3D cube. And faces are what's bound by the set of edges. They represent the surface. So for example, the front-facing square is a face. With modeling for 3D printing, the faces are often triangulated, or they're cut up into triangles instead of being square. So the vertices, the edges, and faces are the types of data you would need to store to have a 3D file to represent your 3D model. An STL file is a popular format to contain all that information about the vertices, the edges, and faces. Here we have an ASCII version of the STL file, and as you can see, it's just text. It's essentially a text file with numbers indicating coordinates for the vertices. There is a binary version of STL, which is just compressed of the ASCII STL. So here we take a look at this first block. This block represents the face that's highlighted in blue, the triangular face on the bottom of the cube. And each one of the highlighted vertex maps to one of the vertices on that bottom of the cube. You might notice there is a normal up here. It might be a little hard to see. But aside from vertices, edges, and faces, every face has a normal. What this means is every face has a sidedness to it. It has an inside and an outside. And the direction of the normal is a vector, is what the outside of the face is. So here, for example, we have the normal being 0, 0, -1, which is 0 in the x direction, 0 in the y direction, and -1 in the z direction. So this normal vector points downwards. And this is assigned to this face on the bottom of the cube, which makes sense because since the normal correlates to the outsidedness of the face, you want your outside of the bottom face of your cube to be downwards. So if you know all the coordinates of your imaginary 3D model, you can just use your favorite software or favorite programming language to output a text file with a series of coordinates like this and send that off to be 3D printed. Where it gets tedious is, let's say you have your model, but now you suddenly want to scale it up. Maybe you want to scale only a portion of it or rotate a little piece. And now you start writing a lot of mathematical functions. Luckily for you, a lot of 3D graphics software already provide this functionality for you, so you don't have to write it from scratch. There's a lot of 3D graphics software out there. If you come from an engineering background, you might be familiar with SolidWorks or AutoCAD. If you come from graphics, you might be familiar with Maya or 3D Studio Max or even Rhino. Blender is another one of these 3D graphics software, and it's one that I really, really like. It's open source, it's under GPL, and has a very large and friendly community. It has a lot of mailing lists, IRC channels. Feel free to ask questions, and people will be happy to answer these questions. It also has a lot of features aside from modeling and graphics. It has a video editor as well as a game engine. And because it's open source, a lot of people contribute back to it. So there's a myriad of different add-ons. Blender runs on Linux, Macs, and Windows, and it has a Python API, which is what I find really cool about Blender. Its Python API is called BPy. So let's take a look at Blender. So this is Blender when you first start up. It provides a default cube for you to work with when you first start up. You can remove that if you wish. I'm going to hit a button that says scripting. This scripting button is just for setting up my windows, so it allows me to script easier. You can rearrange the windows however you like. This is just a neat shortcut to get set up faster. So I'm going to close one of these windows, and we'll come back to that one later. Instead, you see in the middle, there's a 3D view. It's the same 3D view when you first started. And on the bottom, there's a Python interactive console. So this is like a REPL. You can start typing commands like print hello PyCon, and it will evaluate and print that. So let's start making stuff. Blender provides a lot of stock objects like cubes, cylinder, cones, and a monkey named Suzanne. So you can start creating objects through the UI by hitting Create, hitting a cube button, and then it will pop a cube. Now I'm going to hover over the cube button that I just pressed, and a tooltip will pop up with the Python API equivalent. So I can just enter that command into the interactive console, and it'll do the exact same thing. Blender also provides another neat functionality in that all the actions you do will be logged as their API equivalents, and it will also log their parameters, so you can replicate what you just did very easily. So here, I'm going to type in the command to delete the cube. When I pressed the shortcut to delete earlier, it locked that, And then I'm going to create a cube that's slightly larger with a radius of 5. And the radius was displayed in the log before. Now let's bring back the text editor that I closed before. The window I closed before was a text editor. Blender ships with a rather simple text editor that can load and run scripts. You don't have to use this. You can use your own text editor of choice, and then just load your Python scripts in here. So I do import bpy, which will import the module. And I call the same function as before to create the cube. Since I'm in a text editor, now I can do cooler, more advanced stuff. Like, let's say I want to make a row of cubes. So I am going to create a row of cubes, and I'm going to move them slightly by setting their x location. So here, I'm going to click Run Script, and it's going to create for me a row of cubes. You can save this script, and Blender will actually save a copy of this script within its .blend file. And if the saved script is out of sync from a script that, let's say, you've loaded, Blender will warn you that they're out of sync and prompt you to resync them. So while cubes are fun, let's make something more interesting. Let's make glasses. So here I wanted to take an image of the front of a pair of glasses frames and turn it into a 3D printable model. I want to do this because I want to make it easier to prototype a lot of different styles of glasses frames faster. So I wrote this script that takes an SVG or image vector file of a pair of glasses. I'm going to hit run, and it will act on that image and turn it into a pair of glasses frames that I can print. It has cool little features, like has nose pads, and it has the bridge in the front that's a little bit protruded. So since I wanted to prototype glasses this way, I want to make sure that these glasses I've generated are actually good enough, or rather they're close enough to actual glasses so that it's not completely off from what you're intending on to design versus what your end product is. So here I took the front image of a pair of glasses I already owned. I ran that image through my script to get a 3D printable frame. I printed it out, and I popped the lenses out of my original pair of glasses and popped it into this pair that I 3D printed. And if the lenses fit, I would know that I got a close enough approximate generated from a single front image. So here's me popping the lenses into the pair of glasses. Let's take a look at how you would do this using the API. These are like the very beginning steps to how to get started making your own glasses. So first, I import an SVG vector image. It's a 2D image of a pair of glasses. I'm going to scale it up so it's a little bit bigger. And then I'm going to extrude it so it has a little bit of thickness to it. So here is my Blender application. I'm going to import a pair of glasses. It's very small when you first import it, but if you zoom in, you can see it. Now I'm going to hover over what I would have clicked if I was doing this via the UI, but instead I'm going to call its API equivalent to scale it up. I'm going to scale it up approximately 10 times its original size, just to work with it a little bit easier. Next, I'm going to extrude it. And extrude, which just means it will give it some thickness, so it's, instead of a 2D flat image, it's going to become a 3D figure. So I hover over where I would have typed in a value to extrude it, and instead I'm going to call the extrude from the console. So now there's a little bit of thickness. It's probably rather hard to see on here. So I'm going to change the color of this currently black pair of frames to something more visible. So I'm going to change it to a bright purple color, just so you can see it easier and work with it easier. So there's your glasses. Instead of typing all those in the console, I could have just as easily written all those in a single Python script and then hit run, and in a single click, it's going to do the exact same thing by turning the picture into a pair of glasses. There's a lot more steps I did in my own script, but this is the very beginning steps on how to make your own glasses. Let's back up a minute and talk about the higher level things I just did. So you might have noticed that I typed in bpy.data a lot. And this is Blender's way for you to interact with the data objects that Blender provides. So if I want to, say, change a vertex, the little dots that we talked about earlier that represented points in 3D space, I can go into data, I can change it there, I can grab its coordinates, and I can move them around. You might have also noticed that I typed bpy.ops a lot. bpy.ops represent Blender's operators. Essentially, every action you take in Blender is an operator call. And operators are mode dependent. So Blender is very modal, has a lot of different modes. The ones that you'll probably encounter the most are the object mode and the edit mode. And object mode deals with things that happen to the object as a whole, and edit mode tend to deal with finer details or subcomponents of the model. So when you invoke an operator call, the call itself will do an internal poll to check the state of the application to see what mode they're in. And if it's not in the expected mode, it will fail and throw an exception. Otherwise, it will execute its commands. So some operators are only available in object mode, and others are only available in edit mode. So an example of operator we used was scale. So we talked a little bit about representation. We talked a little bit about how to get started modeling in Blender with the API. We talked a little bit about what bpy.data, and bpy.opsment. Now we're going to talk about how to model with 3D printing constraints in mind. So you can't print every 3D object you can think of. There's a couple different constraints you need to keep in mind. One is your object has to be manifold. And this has a very mathematical definition, but you can think of it as your object needs to be watertight, or has no holes in its surface, or roughly that every edge needs to have 2 faces. If it doesn't follow this constraint, a lot of subsequent processes downstream won't know how to handle the model that you have. So that's one constraint you need to keep in mind. Second one is your normals needs to face outwards. Remember when we talked about normals on the bottom of the cube? So basically, what this means is your the outsidedness of your faces need to be on the outside of your model. If, like, let's say one of them is flipped, that's no good. And lastly, another constraint to think about is you can't have too many vertices. So when we're looking at the cube before, we sort of represented 2 corners of cube as 2 vertices with an edge in between that connected them. We could have easily just as well represented that edge as having, let's say, 10,000 vertices in between, connected by very, very, very tiny edges. And that's a totally legitimate representation, but because of suddenly there's a lot more vertices, it's going to slow down any post-processing that happens. And also, some of the post-processing software won't be able to handle like tens of thousands of vertices. And this is this aspect, this constraint, is very printer-specific and maybe a little bit software-specific, depending on what you use to pass this model information to your printer. So a more visual demonstration of what a manifold is the donut or torus that you see on your right. That's totally available to be 3D printed, even though you see that gaping hole in the middle. It's not a hole in the surface of the model, which is key. Whereas the one that you see on the left, there's this dark rectangle area. And that represents there's missing faces there. So the edges only have one face on one side, and there's just nothing on the other side. And that's not a good model. So Blender provides you with a lot of operators to help you fix your model should you need help fixing. You could use fill or fill holes to fill the missing components, missing faces. You could use make outward normals consistent. So you can use this function to sort of put all the outside of your faces on the outside of your model, sort of define the outside as the outside. Also, you could use a decimation modifier to try to reduce the number of vertices without losing resolution. When you first start 3D printing, there's a lot of tools out there that will sort of fix your models for you, so you don't have to do this yourself. But this is useful, like being able to fix it yourself is useful when those tools don't work. So I have this little figurine I made maybe 2 years ago, and at the time I tried I didn't make this in Blender, but I try to use a lot of different software to help me print this little figurine, and none of them worked, almost none of them. So I tried using NetFab at the time, which is a popular mesh repair tool that's specifically dedicated to repairing models for 3D printing, and that failed. I think Adobe Photoshop was coming out with 3D printing support at the time, and that didn't fix it. I tried using Mesh Mixer at the time. That didn't work either. What worked was Autodesk Print Utility, which is a software to also help you 3D print by Autodesk. But it took 3 hours to run on my laptop to sort of fix this small model. And there was a lot of loss in resolution, which I didn't like. So more recently, I decided, hey, let me try writing my own cleanup protocol. So I went into Blender, scripted some instructions to how I would want my model to be fixed, and it ran in about 5 minutes and produced a completely printable model. So that's the power of being able to write your own cleanup protocol. So we covered a lot in the past 30 minutes. We talked about what is 3D printing, how 3D models are represented. We talked about the Blender API, how to set up scripting, different ways of modeling with the operators, and 3D printing constraints. I hope you've all learned a lot. You've been a great audience, and thank you. Maybe we have time for questions? Questions. I don't know if we have time for questions, but we'll try to do questions.
Just a quick question. Can you recommend any online resources for those wanting to get into fiddling about with Blender and Python?
The question was, can you repeat the question?
Sorry. Can you recommend any online resources for getting started with Python and Blender?
Yes. There's a lot of YouTube videos. I don't know any off the top of my head, but there is a wealth of YouTube videos for basically anything you want to do. You can be like very specific, like I want to make a house, how would I do that? And it will try to people have written like tons and tons of tutorials about that. But also find me afterwards, and I'll try to help you.
Thank you for this. Do you know if there's any straightforward way in Blender to round edges?
Round the edges, yes. So it sort of depends on, okay, so the simple solution is yes, there's a modifier. It will try to smooth your edges for you. But the way it does that is it sort of creates more edges for you, so to round it out. And if you do that a lot of times, you're going to get tons of vertices. But that is a very easy way to make. There is a smoothing function in Blender to try to smooth out your objects.
Thank you.
Thank you for the presentation. I had a question on the SVG file. Currently work for a school, and we have a lot of problems trying to actually either laser scan objects or photograph them and import them. What are you doing? Because we have no problems making, the STL files manually in Blender or MakerBot, but how are you actually acquiring certain images?
The way I make SVG files is I use Inkscape, another open source software. Okay. And Inkscape, you can pass it in like a raster image, like a JPEG or a PNG, and you can say trace outline, and it will do its best to trace its outline and turn it into a vector image.
Thank you.
Hey, thanks for the talk. That was super cool. I was wondering, I didn't really realize, I suppose it makes sense, but I didn't really realize that people were using Blender for 3D printing. I was wondering about when it comes to like, I feel like I've seen stuff about filling objects in different ways. Like there's different strategies for filling the internals of these objects. Like does Blender have stuff that deals with that, or is it just assumed to be solid and that's the end of it?
So if you're printing, I'm trying to understand your question. You're talking about setting like.
So if you have a square.
Yep.
Inside those faces, do you get to say this should be just full of solid plastic, or do I get to say it's empty?
It depends on how you're printing it. So if you have like a square, it's just these sets of faces. When you're actually printing, if you have your own printer, you can specify like a fill type.
Okay.
So you can say like, I want a honeycomb pattern, and your printer is going to like try to fill it in a honeycomb pattern. If you're not printing it yourself and like exporting it to someone else to print, you might have to like sort of generate what the internals would look like before you export this model.
Oh, so it's not necessarily a Blender thing, it might be a printer driver deal?
Specifying the fill of it is more on the printer side of the job. But you can certainly model it to say, I want a solid fill, and I want it to be filled this way by actually generating what the internals would look like.
Okay, excellent, thanks a lot.
All right, thank you.